Hello, I'm Derek Gunny, and this is my video presentation for the C111 final project. The objective of my project was to design a supervised learning classification algorithm to determine whether a soil sample was from a burned or unburned forest site. To do this classification, I used a support vector machine model. The dataset used for this project was compiled by Oak Ridge National Laboratory Distributed Active Archive Center. This dataset consists of soil sample data from sites in Canada and Alaska taken from 1986 to 2013. I wanted to focus on the composition of soil over anything else, so I selected 4 relevant features from the dataset to use as an input, which were percent fine nitrogen, percent fine carbon, fine bulk density, and total bulk density. The data was collected in a way such that coarse and fine soil comprising a sample were separated using some methodology, so values like percent fine carbon refer to the percent carbon composition in the fine soil. Anyways, I settled on these and then had to parse through the dataset and remove missing data. This left me with about 1,700 samples to work with, which wasn't too bad. I went ahead and plotted the data in 3D feature space in a couple different ways, of course, each of which had to leave out one feature. This data, as you can see, was very clumped, and there wasn't any clear boundaries between the data, so I decided that using the radial basis function as the kernel for my support vector machine was the way to go. The plan was to use the scikit-learn library for coming up with the support vector machine model, where I could set the kernel to be RBF, yet I needed to establish 2 parameters myself. Those were the regularization term C and gamma. To get the best possible values for those parameters, I did a grid search, which checked the performance of models based on numerous permutations of gamma and C, and it ultimately spit out an optimal C of 100,000 and gamma of 0.1. With those parameters established, I was ready to train the model, and this was really quick. I used the Plotly library to come up with these interactive plots of the test set data in 3D feature space. I've colored the data so that the orange and yellow dots were misclassified instances. The yellow dots were samples from unburned sites predicted as burned, and the orange dots were samples from burned sites predicted as unburned. As you can see, the model made the most misclassifications where the 2 groups were the least distinguishable. And in the 3D feature space here, it was this big, bulky region of data. On the plus side, the fact that there are similar amounts of yellow and orange dots reveals that this model wasn't really favoring one classifier over the other. It wasn't just guessing that every sample was from a burn site or vice versa. Instead, it took a stab at guessing both and at times was wrong for both. The 2 error metrics I chose to evaluate my model with were accuracy, as in the percent of test instances it got right, and the F1 score, which tethers precision and recall. Because the sample size was low, the accuracy of the model would change when reshuffling the training and test data. So I trained a model 200 times with a for loop using different training data each iteration so that I could see the fluctuation of accuracy and the F1 score. As the figures show here, accuracy and the F1 score did fluctuate, but there was a pretty clear mean for both. These error metrics ultimately highlight that the model performed pretty well. Still, there's room for improving this model, and I think that would start with incorporating some existing physical relationships into the model. For example, relating nitrogen composition with the depth at which the sample was gathered could be pretty meaningful. And yeah, that's it. Thanks for listening.